Um, okay, so hello everyone. Well, in this video, I will make an introduction into how we can use superposition, the superposition principle to solve AC circuits. Okay, this is very useful, in particular when you have different elements in your circuits that operate at different frequencies. For example, you can observe here that we have this current source that has a frequency omega equal to 6 radians over second. But also we have a voltage source that has a frequency, okay, of 2 radians over seconds. So we cannot convert all the elements into the frequency domain. In this way, convert the resistance and the inductor that this circuit has into the frequency domain directly because we have two elements that are operating at a different frequency. And also the problem is asking us to compute the voltage Vx, okay, the voltage that is in the 16 ohm resistor. So that's why we need to find another approach in which we can use the phasor representation and impedances in order to calculate this voltage. The problem, as I mentioned before, is that we cannot compute um, all the elements in the circuit into the frequency domain directly because we have these two sources that have different frequencies. So the idea of the superposition principle is to analyze what is the individual contribution of each of the sources to the voltage Vx. Okay? So to analyze the individual contribution of each of the sources in the circuit, what we can do is to assume that only one of the sources is on and the others are off. Okay? So for example, let's say that the current source, okay, this current source, no, the current source is off. Okay? So since the current source is off, we can rewrite the circuit as follows. So we can express the circuit as follows. Since the current source is off, we can model this as an open circuit. Okay, so here we have the current source that is off, and since it is off, we can model that as an open circuit because in an open circuit, there is no current flow. That's why we say that when the current source is off, this can be represented as an open circuit. And also we have here the 16 ohm resistor. Remember that we need to compute this voltage in the 16 ohm resistor. And also we have here the 20 ohm resistor. Okay, and here we have the inductor of 5 henries. And here we have the voltage source. Okay, that has a value of 50 times the sine of 2 times t volts. Okay. So since here we have an open circuit, there is no current flow. In fact, we can remove all this part, or there will not be current that is flowing through this part of the circuit because here the resistance is infinite. Okay. What we can do is to analyze what is the voltage contribution of this voltage source into the 16 ohm resistor. Okay. So I will label the voltage in the 16 ohm resistor for this circuit in which we are assuming that the current source is off as Vx1, okay? And what we can do is now, since only this voltage source is on, we can compute the impedances of all of the elements, okay? So for example, the impedance of the 5 Henry's inductor, okay, is equal to J times omega times L, and this is equal to J. And omega, since only this voltage source is on, is equal to 2 radians over second. So here we have a 2 radians over second, and we multiply this by the value of the inductance, that in this case is 5 henries. And this is equal to 10 J ohms. Okay? And well, we also need to compute the phasor of the voltage source. So here we have 50 times the sine of 2 times t volts. And remember that we need to convert the sinusoidal into a cosine to obtain the phasor. So we need to subtract minus 90 degrees to the argument to convert this into a cosine function. So here we have 50 times the cosine of 2 times t minus 90 degrees. And these are amperes, okay? Sorry, these are volts. I get confused. Okay, so these are volts. And the phasor of this thing is equal to 50 with an angle of minus 90 degrees volts. Okay, so this is the phasor of the voltage source, and the impedance of the resistance are the same. So we don't need to perform any conversion on that. So here we have the open circuit due to the current source that is off. Here we have the 16 ohm resistor. Here we have VX1. Here we have the 20 ohm resistor. Here we have the impedance of the inductor that is 10 J ohms. And here we have the voltage source that is 50 with an angle of minus 90 degrees volts. Okay. Now, what else we can do? Well, what we can do is to apply the the Kirchhoff, no? We can apply the Kirchhoff voltage law to this loop of the circuit. Okay, here we have a loop. And let's say that there is a current that is flowing that I will label as I1. Okay, so if I apply the Kirchhoff voltage law to this loop, I will obtain the following. Here we have minus 50 with an angle of minus 90 degrees volts, okay, plus I1 times the voltage drop in this element. Okay, so we have I1 times 10 J ohms plus I1 times 20 ohms, okay, plus 16 ohms times I1, and this is equal to 0. So remember that the Kirchhoff voltage law states that the addition or the sum of all the voltages within a loop should be equal to 0, okay, within a closed loop. So that's why I'm adding the voltage drop in each of the impedances. And well, the voltage provided by the voltage source. And I am placing here the negative sign since the current direction that I propose is moving from the negative to the positive terminal, no, according to this direction. So that's why I place this negative sign. And remember that we want to compute Bx1, okay? So Bx1 is equal to 16 ohms times I1, okay? So what we can do is to solve this equation for I1, okay, since we only have one incognita, and we will obtain a current I1 that is equal to 1.3382 with an angle of minus 105.5241 degrees, and these are amperes. Okay, and so Bx1 is equal to 16 ohms times I1. Okay, I1. So this will be equal to 21, okay, 0.0 41.15 with an angle of minus 105.5241 degrees, and these are amperes. Okay, so this is Vx1. And we can also represent Vx1 in the time domain as 21.4115 times the cosine, okay? Remember that the frequency was 2 times t minus 100, 105.5241 degrees, and these are volts, okay? And well, I think that's it. So we have computed what is the contribution of this voltage source for the voltage in the 16 ohm resistor. Now we need to make the same for the current source, okay? And we will assume that the voltage source is turned off. So if we rewrite the circuit again, okay? So we can rewrite the circuit as follows. Now we will have that this current source is on, okay? So I will write it as 12. Let me erase this a little bit in order to have more space. So here we have the current source that is 12 times the cosine of 6 times t plus 10 degrees, and these are amperes, okay? And here we have the 16 ohm resistor, okay? This will have a voltage Vx2, okay? Here we have the 20 ohm resistor, and here we have the inductor of 5 henries, okay? But now the voltage source that is in this region is turned off. So to model that, we write or we redraw the current source, sorry, the voltage source as a cable, okay? And we are using a cable since purely cable, we assume that this has no voltage drop. Okay, that's why we use a cable when we say that the voltage source is turned off. Okay, now what else we can do? Well, we can apply, for example, nodal analysis to compute the voltage Vx2. Okay, but to do that, what we need to do first is to convert all the elements into its impedances, because the frequency is now of 60 radians over second, okay? Since the frequency of this element is different, we need to compute again the impedances. But the only impedance that will change is the impedance of the inductor, that is 5 henries, and the impedance of that is j omega times L, and this is equal to j times omega, that is 6, times the inductance, that is 5, and this is equal to 30 j ohms, okay? And well, we can rewrite the circuit into the frequency domain. So for example, here, this current source will be equal to 12. It is already in cosine form, so we only need to take the amplitude and the angle, the phase angle, to express it as a phasor. And now we have this voltage of the 16 ohm resistor that I label as Vx2, the 16 ohms. And we have here 20 ohms, okay? We have here the impedance of the inductor, that is 30 times j ohms. And here we have a cable. And we can, in fact, we can solve this using nodal analysis. We have the reference node, that remember that always has a voltage of 0 volts. And we have another node. Well, this is one of the nodes, okay? And we have another node right here. In fact, we only have one node, no, or one relevant node. And we have a voltage V1, okay? But what else we can compute? Well, in fact, if you analyze the difference in voltage between node number 1 and the reference node, V1 minus 0 volts, you can notice that this difference in voltage should be equal to Vx2. So we say that V1 is equal to Vx2. Okay? Now we can apply the Kirchhoff current law to node number 1, okay, for node number 1. And you can observe that the current source is entering this node. Now we have 12 with an angle of 10 degrees, amperes, and the current in this part should be equal to the currents that are leaving. So for example, here we have a current that is leaving that I will label as I2, and also the current that is flowing through the 16 ohm resistor, I will label as I1, okay? And in fact, I1 is equal to the voltage in the 16 ohm resistor divided by the resistance. So this is equal to Vx2 divided by 16 ohms. And I2, okay, is equal to the difference in voltage between node number 1 and the reference node. And remember that the voltage in node number 1 is equal to Vx2 minus the voltage of the reference node, and we can divide this by the impedance. And the impedance, we can compute the equivalent impedance between these 20 ohm resistors and the impedance of the inductor, and this is equal to 20 ohms plus 30 j ohms. So I2 is equal to Vx2 divided by 20 ohms plus 30 j ohms. Okay? So remember that we were applying the Kirchhoff current law, okay, to node number 1. So, for example, I1, well, the current that is entering is the current of the current source, and the currents that are leaving are I1 and I2, okay? And we have here 12 with an angle of 20 degrees amperes, and this is equal to I1, that is Vx2 divided by 16 ohms plus Vx2 divided by 20 ohms plus 30 j ohms. Okay. So what else we can do? Well, we can solve this equation for Vx2. And Vx2, if you solve this equation, will be equal to 147.7259 3 with an angle of 26.50 43 degrees, and these are volts. And we have the contribution of this current source into the voltage of the 16 ohm resistor. And we can write, and what the superposition principle says is that we can at the end add the individual contributions of each of the sources. So for example, we can add to know the voltage Vx is equal to Vx1, that is the individual contribution of the voltage source, plus the voltage contribution of the current source, that is Vx2. Okay, so we can say that Vx in the time domain is equal to Vx1, that is 21.41 ones times the cosine of 2 times t minus 105.5241 degrees, and these are volts, plus the voltage Vx2, that in the time domain we can express it as 147.72 59 times the cosine of 6 times t. Remember that bx2 has a different frequency. That is the frequency of the current source. Plus 26.50 50 and 4 degrees, and these are also volts. Okay, so this is the result. Okay, so in this way we can solve a circuit. Let me go back a little bit. We can solve a circuit that has two sources that operate at different frequencies using the superposition. And basically we analyze individual contribution of each of the sources into the voltage or current that we want to compute, and then we can add together the results in a similar fashion that I presented in this part. Okay, so that's all for this example. I hope it was clear, and see you later.